Welcome back once again. Today to start off the new unit, we're going to start with a brainstorm question. Okay, I'm going to show you a few pictures and you're going to tell me, or tell the forms, what you think these have in common. So the first picture is toilet paper. Very important use in lots of houses. So what is a toilet paper and someone opening a door, someone driving, and someone doing a freeze, which is like a breakdance move, okay? Just like not moving, doing some funny shape on the floor. What do all these pictures have in common? Think about it for a bit. Pause the video if you need to, and write out what you think all these have in common. Okay, so, let's see. One thing this toilet paper have in common is when you pull it, it starts to turn. Interesting. How about the door? When you're opening a door, you press down on the handle, the lever, okay? So you're pressing down, and then it unlocks, and then you pull the door, so the door kind of swings out. I'm going to draw that thing. From the top view, door is closed, swings out, door is open. Last one. If you're driving or learning how to drive, driving is a lot of turning the wheel. So you're going to turn it to the right. Sometimes you'll push it up. Okay, all kinds of turning stuff on the wheel. And lastly, this is a tricky one. What does this person have to do in common? Well, this person's not falling down or not hitting his head, not hitting his legs. So somehow, the turning force on this side is equal to the turning force on the other side. Let's use red color so you can see it clearer a bit. Okay, so somehow these are balanced, so it doesn't fall. But notice what all the arrows are in all these pictures. It's something to do with turning, okay? Toilet roll is turning, handle is turning, door is turning, wheels are turning, person is not turning, thankfully. But all these turning ideas are because of moments, what we call that. So this whole unit will be looking at turning forces, moments, torques, and what all those mean.
So, turning forces or forces that causes rotational motion. They are given the term torque and sometimes moment of forces. Well, you can use these two terms interchangeably. Personally, I prefer torque, okay? But sometimes you will see moment of forces, and this will have the symbol of tau, okay? So it looks something like this. All right. So any force that causes rotational motion can be known as a torque. But we define torque or moment of force as the product of force and perpendicular distance. So it's product of force and perpendicular distance from a pivot, or rather from a point. Okay, so you can't define torque as a force that causes rotation because that is too general. Okay, so torque is actually a mathematical definition, right? So if we want to write this in equation, your torque is equal to F times D, okay, where F is 90 degree to D. All right, these two are actually vectors. So later on, if you can have time to study about cross products, these two are actually cross product of vectors. But for our purposes right now, we're going to stick to force times perpendicular distance from a point. All right, so this is the definition. This is the equation. I know what you're thinking. Teacher, you see the diagram down there? Oh? The force not like how to find. Okay, you chill first. First things first, we need to look at the point. This point here is oftentimes the pivot. Okay, so if you can identify the pivot, that would be helpful. So we're going to first choose a few examples where the pivot is like super obvious. Okay, like for example, this is like a door. All right, so you will see that there's a hinge here, and for some don't know why I decided to pull the door with a direction of force, with force in this direction here. Miss, why you do this? Yeah, just because lor. So my torque here will not be equal to F, the value of F times D. Teacher, why? My dudes, you see, this is the hinge here. I'm just going to draw a big cross here for the hinge. This is not 90. So if it's not 90 and the vector is not in the direction that you want, do you remember what to do? If your vector is not in the direction that you want, I know, we resolve the vector. So we're going to split this force into two. So this angle here is labeled as x. All right, I'm going to change this angle to something that maybe we're a bit more used to. So this will be theta. Okay, so I will resolve my force, one in the vertical direction. It doesn't have theta, so I'll call this F sine theta. And I'll resolve another component here. This one is F cos theta. All right. So the torque on this bar, let's say I call this bar A, is equal to F sine theta, because F sine theta and the hinge H is already 90 degrees, times D. All right. So you resolve your forces. This is the most straightforward way because you have a point and you know you want to orientate such that it is 90 degrees. All right. We will do some exercises later. So this is one technique. You can always, resolve the forces. Another technique is you can find the perpendicular distance. Teacher, what do you mean by looking for the perpendicular distance? Well, let me show you a geometry. So I'm going to extend this line of force a bit to the best of my ability. So which is what I'll suggest you do. If let's say you can't really see where the perpendicular distance is, I will extend this until somewhere maybe here. Okay. And I will build the perpendicular distance from this line of action till the point H. Okay, sorry, I infringe in the bottom diagram a bit. Okay, so I can tell that now the perpendicular distance is actually here. Here to here is my D. Let's say this perpendicular distance, I call it X lah. So if we do alternate angles, theta is here. I transfer over, theta is here. So this now becomes my perpendicular distance. I can obviously find X in terms of D. Okay, so from this right angle triangle, see the right angle triangle here, this one, and the bar, the whole length of the bar is D, right? So I can actually say something along the lines of sine theta is equal to opposite, which is X, over the hypotenuse, which is the length of the bar. Teacher, conspiracy. X is D sine theta. Yep. So you can take torque as this value of force here, this F, okay, multiply by the perpendicular distance here to here to here. Okay, so force is in this direction, multiply by the distance that is 90 degrees, this one. Okay, force times perpendicular distance. I mean, that's the intention of you drawing that long line. All right, so I can take just F multiply by D sine theta. So there are two techniques. Number one, we resolve. Resolve and use the perpendicular component of force, which is the cleanest way to do. But sometimes you may want to be able to find the perpendicular distance directly. Normally, using right angle triangles and transferring angles. So that part, I leave it to you. It's a free world. Different people got different choices. But normally when we do examples, Miss Ellie and I will only do one. All right. So let's look at a very, very simple example like this one. Okay. So this is another bar. You have a length 2 meters. And then this one is pivot at this point. Okay. So this is the only time I will do both methods. Okay. So if this is pivot at this point, all right, I can obviously resolve my force. By the way, right, do you know that the rotation can be clockwise and counterclockwise? Let's go back to this one. This F will cause the whole bar. You see, let's say this is my bar. Okay, and I pull it up. Okay, so my pivot, my hinge is here. No, my hinge is here. Okay, and then I pull it up. So this thing is going to rotate counterclockwise like this. All right, rotate counterclockwise. Whereas this one will rotate clockwise. So again, you have two options. You can resolve. This one will have a component of F opposite the angle, sine 45. Okay, and you will take the perpendicular distance. So the torque here will be equal to F sine 45 times 2. Okay, you may be thinking, teacher, do we really can we really ignore this F cos 45? Well, ladies and gentlemen, this F cos 45 will pass through the pivot. So if you draw out the line of force for this F cos 45, it passes through the pivot. So there is no torque. It's a bit like you want to open the door, right? Let's say this is your door. You want to open your door. And then you go apply force like that. Or you want to open your door. Let's say this is your hinge. Hinge is here. Hinge is here. And then you push the door like that. Walao, sliding door, man. Sliding door is not rotational motion already. Sliding door is a different chapter, okay? So in this case, there is no torque because there's no perpendicular distance. I'll write that down for you. This one is no torque or no moment of forces because the line of force passes through the pivot. So there is no perpendicular distance. Or perpendicular distance, it passes through the pivot directly. Okay, so these are examples of no torque. Okay, so if let's say the line of action of force passes through the pivot, then there is no torque. Okay, because there's no perpendicular distance. Okay, so this is what torque is. A few other things regarding to moment of forces. Number one, sometimes the general equation generally can be written as torque is equal to Fd sine theta. Okay, so your cases could be theta is equal to 0. That means F and D is parallel. Example like the cases that I draw on top here. Okay, like this one. You could also have cases where theta is equal to 90. Okay, theta equal to 90, very nice. Okay, because sine 90 is 1. So in these scenarios, you don't really need to resolve anybody. Correct? Normally your hinge here and your force will either be in this direction or in the opposite direction. Okay, maybe they have another force lah. Let's say this F1, then the other one F2 here. Can I not? But F1 will turn clockwise. Okay, F2 will turn counterclockwise. Is it clockwise? Oh, they are both clockwise, sorry. Maybe I should put F2 here. Like that. F2 counter? Yes, counterclockwise. My bad. Sorry, yeah. Brain a bit hang. So F1 will turn clockwise. F2 will turn counterclockwise. Like this. Okay. So because they are turning in opposite direction, we need to give them signs one. So maybe clockwise, we put positive. Clockwise moment. Or clockwise torque. And then this one will be negative. Anti-clockwise. Of course, as usual, the positive, negative sign, up to you. All right. So, and then sometimes we can have the third case. Okay. So this is case number 1A, case number 2B. You can also have case C. All right. Case C is the general one where I can apply force in any direction I like. Okay. So maybe this is my hinge. H. And then I apply force like that. Just for fun. Okay. Maybe this is F1. So the theta is between here and here. All right. If you're wondering where the D is the length of the rod. Measure from the pivot. So right now, in this case, this one will be F1 sine theta multiplied by D is equal to the torque. Okay, and because this is counterclockwise, if we follow the previous convention, this will be negative. So torque will be negative F1 sine theta times D. Okay, so whether you need to resolve or not, if you can mentally do, that's okay. If not, feel free to resolve. No harm in that. F1 sine theta. Okay, so like in this case, F2 will have to multiply with D2, and F1 will have to multiply with D1. Here to here, D1. But they're all 90 degrees. Okay, so it depends on the angle and also the direction that the forces is directing. But this is the general equation. You can use torque is equal to Fd sine theta. Okay, this is case 1. But we have another term in our title that would be couple. All right, so what is a couple? Teacher, I know what's couple lah. My girlfriend, my boyfriend, my BFF. Okay, sure. Couple. Couple, the word couple means there is a pair of forces that causes rotational motion. Okay, so you can think about couple as having is a subset, okay, as a subset of torque. So couple is often observed in objects such as steering wheels. So for example, maybe I draw a steering wheel here. Okay, this is a steering wheel. All right, and normally when you apply force on the steering wheel, it will be like, well, maybe I want to turn the steering wheel clockwise. Let's say I want to turn the wheel this way. So what will you do? You will pull here, let's say with the force F. So you pull in this direction. And you will push here. This one is F. So the condition of couple, number 1, condition, they must be the same magnitude of F. Okay. Number 2, they must be opposite direction. Teacher, this one nothing to do with Newton's third law, okay? If Newton's third law happens to give you a couple, that is a consequence. So opposite direction. Okay, and number 3, causes rotation. Okay, causes something to rotate. Like for example, this one will rotate in the clockwise direction. But teacher, how do we calculate? Like, where is the pivot? Like, so this steering wheel is going to spin, right? We can assume the pivot is here or the hinge is here. I'm still going to call this H, okay? So let's say this is the radius R of my circular disc. Here to here is R. You can see R and the line of action of F is 90 degrees. So the torque here, I can calculate using F times R on one side plus F times R on the other side, because both also cause it to rotate in the same direction. So from here, this torque will be equal to F times 2R or F times D, where D is the diameter of the steering wheel or the disc or whatever it is that you are spinning. This is D. So a couple is something that acts on an object in pairs. There are 2 pairs of forces, must have a pair. If you don't see a pair, not couple already, confirm not couple. Okay? Physics not that inclusive. So we need a pair. 2 forces. Same magnitude, opposite direction, and it causes rotation. Same pair. Alright. So when we want to calculate torque, we can for couple, we can just take force times perpendicular distance, but sometimes we may want to do a bit of shortcut. We can take F times D, where this one can be written as force times the perpendicular distance between the couple. Okay, it will be the force times perpendicular distance between the couple. So this is case 2. In other words, all couple have torque, but not all torque are couples. Okay, so you can see, let's say this is all couples must have torque, but not all situations where there are moment of forces are a couple. Okay, so don't get that confused. It's the same thing. It's just a special case that we often see in the real world where we have a pair of forces. Like your hand turning a steering wheel. Teacher, I can turn with one hand. Sure. But, in most cases, sometimes we will apply rotational motion like pulley systems. So that's why we isolate out the idea of couple. So for couple, to find the torque, you can take force times perpendicular distance between the couple. Or you just, like, teacher, is the same thing. I just remember this one can already. Can. This torque is force times distance sine theta is a general equation. All right. So before we move on to some calculation examples, right, I want you to see that this one is a vector. So I'll make a few notes here. Torque here is vector. Teacher, how you know it's vector? Because got direction. You turn clockwise, you turn anti-clockwise, all different direction, right? And number two, the unit for torque is Newton per meter. Okay? So this is the important thing. You should know what torque is, how to define, product of force and perpendicular distance. All right? And know how to calculate given different scenarios. I will see you in the examples.